From the moment we first looked up at the night sky and wondered what lies beyond the sparkling stars, our imaginations have been pulled toward extremes. Among the cosmic extremes, few things capture our curiosity more than black holes. These invisible objects at the hearts of galaxies or drifting silently through the Milky Way are places where gravity is so strong that nothing, not even light, can escape. In science fiction, we often depict them as hungry monsters gobbling up anything that strays too close. In reality, black holes are governed by the same laws of gravity that hold our planets in orbit around the sun. They are not cosmic vacuum cleaners roaming around and sucking up everything in their path. Yet the idea of a rogue black hole entering our solar system is the stuff of both nightmares and wonder. What would it be like if such a cosmic interloper came barreling through our celestial neighborhood? How would the delicate dance of planets, moons, comets, and asteroids respond? And what would the experience be like for life on Earth? Exploring these questions pushes our understanding of gravity, orbital mechanics, and the fragility of the environment that allows us to exist. This thought experiment isn't just for thrill seekers. It reveals much about the nature of black holes, about how gravity works over different distances, and about the extraordinary luck that allows a small rock around an unremarkable star to host life. Neil deGrasse Tyson often reminds us that the universe is under no obligation to make sense to us. By imagining unlikely scenarios, we learn to appreciate what is actually happening and to test the edges of our theories. Black holes are ubiquitous in the cosmos. Supermassive ones anchor galaxy centers. Stellar mass black holes, the remnants of collapsed massive stars, orbit quietly in binary systems or drift through interstellar space. There are even hypothetical primordial black holes, perhaps formed in the early universe, that might be the size of mountains but with the mass of planets. Most of these objects are incredibly far away. For billions of years, our solar system has traveled around the galaxy without a close encounter. But given the vast timescales and the number of black holes, a close pass is not impossible. Grappling with that possibility leads us to examine gravity, not just as a force that binds, but as a sculptor that can twist orbits, trigger chaos, and worlds. Before we imagine a black hole paying a visit to our cosmic home, we need to understand what a black hole is. A black hole is a region of space where matter has collapsed to such a density that the escape velocity, the speed required to leave its gravitational pull, exceeds the speed of light. The boundary around this region is called the event horizon. Once something crosses this boundary, there is no turning back. At the center, general relativity predicts that the curvature of space-time becomes infinite, a point called a singularity. Black holes are defined not by what goes on inside, but by their mass, charge, and spin. Stellar mass black holes form when stars with more than about 20 times the mass of our sun exhaust their nuclear fuel and collapse under their own gravity. Supermassive black holes, millions to billions of times more massive than the sun, reside at the centers of most galaxies. Between these two extremes lie intermediate mass black holes, and at the hypothetical lower end are primordial black holes, perhaps with the mass of an asteroid or a planet. The gravitational influence of a black hole is determined by its mass and distance. At a safe distance, the gravitational pull of a black hole is no stronger than that of a star of equal mass. Only when you get close do its extraordinary properties manifest. What makes black holes so unusual is not just their mass, but their density, because that mass is squeezed into such a small volume. The gravitational gradient, the difference in force between one side of an object and the other, becomes extreme. This gradient gives rise to tidal forces that can stretch or compress. When an object such as a star or a planet approaches too close, the difference in gravitational pull between its nearer and farther sides can rip it apart in a process known as spaghettification. Imagine an astronaut falling feet first toward a stellar mass black hole. The force on their feet could be thousands or millions of times greater than the force on their head, stretching them into a thin strand of plasma. This stretching happens outside the event horizon in small black holes because the gravitational gradient increases rapidly as you get closer. Around supermassive black holes, the gradient is gentle at the event horizon, so an object could cross the horizon intact, only to be torn apart deeper inside. In addition to stretching, gravity can also compress. Near supermassive black holes, tidal forces can flatten stars like pancakes, a phenomenon known as pancake detonation, which leads to bursts of thermonuclear energy. These effects underscore how gravity, ordinarily perceived as a gentle tug, becomes a violent sculptor in extreme environments. Another peculiar aspect of black holes is how they affect time. According to general relativity, massive objects curve space-time, slowing the passage of time in strong gravitational fields. Near a black hole, time for an observer close to the event horizon slows relative to someone far away. If you hovered near the horizon, clocks on Earth would tick much faster. From Earth's perspective, an object falling toward a black hole appears to slow down, its light becoming redder and fainter until it freezes at the horizon. From the falling object's perspective, time would seem normal as it crosses the horizon and continues inward. This gravitational time dilation isn't just a theoretical curiosity. It has been measured around Earth using atomic clocks on airplanes and satellites, but near a black hole, the effect is dramatic. Combined with extreme tidal forces, time dilation makes the experience of approaching a black hole unlike anything else in the universe. With these ideas in mind, let's return to our solar system. The sun holds about 99.8% of all the mass in the solar system. Its gravity keeps the planets, asteroids, comets, and ice in the Oort cloud locked into their orbits. If you could magically replace the sun with a black hole of the exact same mass, the gravitational pull on the planets would remain the same. Earth and the other planets would continue to follow the same path because gravity depends on mass and distance, not on whether the mass is in the form of a glowing star or a dark hole. We would not suddenly spiral inward or be sucked away. Instead, we would continue orbiting an invisible object. The major difference would be the absence of light and heat. Within 8 minutes, the time it takes light to travel from the sun to Earth, the sky would go dark. Temperatures would plummet, photosynthesis would halt, and within weeks, the surface of Earth would begin to freeze. Our atmosphere might condense, and oceans would turn to ice. Eventually, geothermal heat and radioactive decay would keep the subsurface warm, but the surface would become a frozen wasteland. In this scenario, gravity itself does not doom us. It is the loss of energy from the sun that matters. So, what about a scenario in which a black hole doesn't replace the sun, but wanders in from afar? To understand the consequences, we must consider the mass of the intruder and its trajectory. Black holes range from a few solar masses to billions of solar masses. A supermassive black hole would have such a wide event horizon that if it approached, its gravitational influence would be felt long before it reached the inner planets. A stellar mass black hole is smaller and has a smaller sphere of influence, but its gravitational gradient could wreak havoc if it came too close. Primordial black holes, if they exist, might be much smaller. They might pass through the solar system with minimal effect. For example, some scientists have hypothesized that if dark matter is made of primordial black holes, many could pass through the inner solar system over millions of years. Their gravitational pull would be minute, only producing tiny wobbles in planetary orbits that would be difficult to detect. The bigger threat lies with a black hole of several solar masses passing within a few dozen astronomical units of the sun. The key factor is distance. Gravitational force diminishes with the square of the distance. A black hole outside the Kuiper belt would tug on comets more than on planets, while one venturing closer would have progressively greater effects. At the distant frontier of the solar system lies a shell of icy bodies known as the Oort cloud. This reservoir of comets extends tens of thousands of astronomical units from the sun. It is loosely bound by the sun's gravity, so the orbits of its constituents are easily perturbed by passing stars or molecular clouds. Astronomers believe that stars passing within a light year of the sun occasionally jostle the Oort cloud, sending comets into the inner solar system. If a black hole with several times the mass of the sun passed through the Oort cloud, its gravitational influence would be like that of a wandering star, but stronger. It would disturb the orbits of countless comets, sending a rain of icy bodies toward the inner solar system over thousands or millions of years. Some comets might collide with planets or the sun. Others might slingshot around the intruder and be ejected from the solar system entirely. The immediate effects might be subtle, but over time, the increased comet flux could lead to more impacts on Earth. While individual comets pose local hazards, the greater risk would be long-term climate change caused by repeated impacts. The geological records suggest that large impacts have contributed to mass extinctions and climate shifts. A black hole in the distant solar system would thus serve as a cosmic acoustic, stirring up the quiet outer reaches and altering the inner region indirectly. As the black hole moves closer, the gravitational stakes rise. Suppose the black hole passes just beyond the orbit of Pluto, about 100 astronomical units from the sun. According to astrophysicists, at this distance, the orbits of Uranus, Neptune, and Pluto could begin to change. These planets would feel the tug of the intruder enough for their paths to lengthen or shorten or even become slightly inclined. Earth, however, would still be far enough away to remain largely unaffected. Our seasons, climate, and tides might not change perceptibly, but the outer planets could shift in subtle ways that would, over tens of thousands of years, propagate inward. The gravitational influence of the passing black hole could also rearrange the Kuiper belt. Objects might be ejected, collide, or be sent into new orbits. Astronomers have speculated that unusual orbits of some distant objects might hint at a massive unseen body. Some even wonder whether the hypothetical Planet 9 might be a small black hole. If a black hole passed near Pluto, it could mimic such an effect, clustering the orbits of distant objects. The key point is that at large distances, a black hole's gravity is not a death sentence. It is simply another mass in the cosmic dance, albeit a heavy one. Now let's move our interloper closer, between the orbits of Uranus and Pluto. At this distance, the gravitational tug on the outer planets becomes significant. As astrophysicist Sarah Vogel explained, if Uranus and Pluto were passed by a black hole at close range, they might be captured by its gravity and begin orbiting the black hole instead of the sun. The reshuffling of the outer planets would alter the solar system's gravitational balance. Earth's orbit could change gradually as the gravitational forces of Jupiter and Saturn responded to the new arrangement. Seasons could shift, the length of the year might change, and the angle of Earth's axial tilt could vary. A small change in orbit could move us slightly closer to or farther from the sun, altering the amount of sunlight we receive. A change toward a more elliptical orbit might lead to extreme seasons with hotter summers and colder winters. An inward shift could heat Earth, while an outward shift could plunge us into an ice age. Life is finely tuned to the present conditions. The gravitational intrusion of a black hole could disrupt this equilibrium without even coming near Earth. The cosmic interplay of masses demonstrates how interconnected the solar system is, and how a disturbance in one part can ripple through the whole. Bring the black hole closer still, within Saturn's orbit. At this range, the intruder's gravitational pull would move Earth out of the habitable zone. Earth could be drawn slightly inward toward the sun or outward toward the black hole. Either way, the temperature on Earth would drift beyond the narrow band that allows liquid water to exist. The direction of the change would depend on the exact geometry and speeds involved. If we moved closer to the sun, we might experience runaway greenhouse effects, causing oceans to evaporate and atmosphere to thicken with steam and carbon dioxide. If we moved outward toward the black hole, we might freeze. Closer to Jupiter, tidal interactions would become noticeable. Tides are caused by gravitational differences across a body, and a nearby black hole would exert a powerful tidal field. Earth's crust could buckle under the strain. Mountains could collapse, and volcanoes could erupt more frequently. Earthquakes could become more intense as the moon responded to the changing gravitational environment. Our tides would change as well, affecting ocean circulation and climate. The closer the black hole came, the more violent these effects would become. What happens if the black hole ventures within the orbit of Jupiter, or even between Earth and Mars? At this stage, we would no longer be dealing with subtle orbital shifts. We would feel the direct pull of a massive body. Earth would begin to orbit the black hole, or be captured into an unstable trajectory. The shape of our orbit could become highly elliptical, bringing Earth dangerously close to the sun at one end and far from it at the other. The tidal forces exerted by the black hole would cause planetary crust to flex and heat. Our planet could undergo global resurfacing. Entire continents might melt as magma oozed from the mantle. Oceans would boil away. The atmosphere would be stripped or superheated. Any life on the surface would perish long before Earth approached the event horizon. As we approached even closer, the gravitational gradient would become so steep that our planet would begin to stretch. The crust would crack, tectonic plates would be torn apart, and the Earth would be pulled into a stream of debris. This debris would spiral around the black hole, forming a glowing accretion disk of superheated plasma. The debris might emit X-rays and gamma rays as friction heated it to millions of degrees. Eventually, the fragments of Earth would cross the event horizon and contribute to the black hole's mass. To observers far away, our planet might appear to slow and fade, time dilating as the debris approached the horizon. To the material itself, the end would come swiftly as the laws of physics we know cease to apply. What about tiny black holes? Primordial relics of the Big Bang. Some theories suggest that fluctuations in the early universe could have created black holes the size of mountains or even smaller. These hypothetical objects could roam the galaxy unnoticed, forming part of the dark matter that holds galaxies together. Because they are so small, the gravitational influence would be correspondingly weak. A primordial black hole with the mass of a mountain would have a radius smaller than a proton. If such an object passed through the solar system, its gravitational pull on planets would be negligible. Even if one passed right through Earth, it would be more like a bullet than a cosmic vacuum cleaner. The tidal forces would be tiny. However, if a primordial black hole with the mass of a planet lurked in the outer solar system, it could cause the observed clustering of distant trans-Neptunian objects. Some scientists have proposed that the elusive Planet 9 could be a small black hole. Detecting such an object would be challenging because it would not emit light. Instead, astronomers look for its gravitational influence on other bodies. Studies have suggested that if primordial black holes make up dark matter, one could pass through the inner solar system every decade or so. Yet their gravitational signatures would be minuscule. They would not significantly disturb Earth's orbit or pose a threat. The bigger threats come from more massive interlopers. All of these scenarios assume a black hole of several solar masses. What if the intruder were much more massive? A supermassive black hole. Thankfully, such giants are extremely rare outside of galactic centers. The nearest known supermassive black hole, Sagittarius A, sits at the heart of the Milky Way, about 26,000 light-years from us. It is not going anywhere. The chances of a supermassive black hole wandering into the solar system are effectively zero. Nevertheless, contemplating such a case can be instructive. A supermassive black hole's event horizon could be millions of kilometers across. Its tidal forces at the horizon are weaker than those of a stellar mass black hole, meaning Earth might cross the horizon intact. But long before that, radiation from the accretion disk would sterilize everything. The gravitational influence of such a body would rearrange orbits long before it arrived. It would likely tear the solar system apart. While this is a useful exercise in scale, it underscores how improbable such an encounter is. The universe is vast. Distances between stars are measured in light years, and empty space makes close encounters between massive objects exceedingly rare. Now that we've explored the catastrophic, let's step back and appreciate the stability we have. Our sun is neither close enough nor massive enough to become a black hole. It will eventually evolve into a red giant, engulfing the inner planets and then shed its outer layers, leaving behind a white dwarf. There is no realistic path for it to collapse into a black hole. The solar system has enjoyed billions of years of relative calm, allowing life to flourish. Rogue stars and black holes wander the galaxy, but the odds of a close encounter are minuscule. The gravitational field of our galaxy is smooth enough that most stars remain at safe distances from one another. Even when stars pass within a few light years, their effects on the solar system are limited to subtle shifts in comet reservoirs. We have time to marvel at black holes as distant curiosities rather than imminent threats. Yet by imagining improbable catastrophes, we sharpen our understanding and gain perspective on our place in the cosmos. Thinking about a black hole entering the solar system also invites philosophical reflection. We often think of Earth as a stable platform, yet it exists within a dynamic and sometimes violent universe. Life has endured asteroid impacts, supernova radiation, and ice ages. Our existence depends on a delicate balance of distance, gravity, atmosphere, and energy. A slight change in any of these factors could render Earth uninhabitable. Black holes embody extremes of space-time. They reveal the limits of our theories and the unimaginable conditions that exist in the cosmos. Imagining a black hole ripping through our solar system forces us to confront the fragility of our world and the contingency of our existence. Neil deGrasse Tyson likes to remind us that we are star stuff. The atoms in our bodies were forged in the hearts of stars. In a sense, we owe our existence to the same cosmic processes that produce black holes. Supernova explosions that create black holes also seed the galaxy with heavy elements necessary for life. The universe is both destructive and creative. From collapse emerges birth. From the death of stars comes the material for planets. There is also a lesson in humility. The universe is vast beyond comprehension. Our solar system is just one of hundreds of billions in the Milky Way, which itself is one of trillions of galaxies. Black holes dot this cosmic web like punctuation marks, marking places where gravity has gone to extremes. They remind us that the laws of physics apply everywhere, even in conditions far removed from our daily experience. They also remind us that there is still much we don't know. We have never observed the inside of a black hole. We do not know what happens to information that crosses an event horizon. We do not yet have a theory that unifies quantum mechanics and gravity. Considering a black hole in our backyard helps us appreciate the sophistication of our theories and the depth of our ignorance. It underscores the need for continued exploration, both observational and theoretical. In the end, the thought experiment of a black hole entering our solar system is a rich one. Depending on its mass and trajectory, a black hole could range from harmless to catastrophic. A far distant, small black hole might merely perturb comet orbits. A larger intruder near the outer planets could rearrange orbits and alter climates. A closer pass could shift Earth out of the habitable zone, trigger geological upheaval, and spell the end of life as we know it. An even closer encounter would tear Earth apart and feed its remains into a glowing accretion disk. A black hole replacing the sun would leave planetary orbits intact but deprive us of the energy we need to survive. Supermassive intruders are so improbable as to be essentially impossible. These scenarios are not predictions, they're exercises in understanding gravity and appreciating our cosmic circumstances. As we bring this imaginative journey to a close, take a moment to look up at the stars. They are distant, yet they shape the story of our existence. Black holes, for all their menace, are part of that story. They are not lurking monsters waiting to pounce. They are natural outcomes of stellar evolution and galaxy formation. Their gravitational fields teach us about relativity, their shadows test our theories, and their role in cosmic evolution links the vast with the intimate. Pondering what would happen if a black hole entered our solar system can be both unsettling and awe-inspiring. It reveals the delicate conditions under which life thrives and the cosmic forces that could disrupt them. It also reminds us that we live in a universe governed by understandable laws that allow us to predict, imagine, and prepare. In the words of Neil deGrasse Tyson, the universe is under no obligation to make sense to us, but through curiosity and science we can make sense of the universe. And in doing so, we find our place amid the grandeur, precariously perched on a pale blue dot, orbiting a star that, fortunately for us, is in no hurry to turn into a black hole or be visited by one. Perhaps the most profound takeaway is one of gratitude, the fact that our solar system has remained undisturbed long enough for consciousness to arise is a cosmic gift. While we cannot rule out every danger, we can appreciate that the universe is, for the most part, not a malevolent place. Gravity binds, but it also allows stability. Black holes are not marauders by nature. They're quiet participants in the cosmic symphony. They help shape galaxies, drive jets of energy, and teach us about the boundary between the known and the unknown. By engaging with them through thought experiments, we learn not just about astrophysics, but about ourselves. We learn to cherish the ordinary warmth of sunlight, the steady rhythm of seasons, and the delicate arcs traced by planets. So the next time you hear someone ask, what would happen if a black hole entered our solar system? You can answer with both scientific insight and poetic wonder. It would depend on many factors. It is extraordinarily unlikely, and the very act of asking reveals our deepest yearning to understand our universe. That curiosity is perhaps our most powerful tool for navigating a cosmos that is vast, beautiful, and filled with mysteries yet to be uncovered. Astronomers have developed sophisticated tools to detect rogue black holes long before they pose a danger. When a compact object passes in front of a distant star, its gravity can act as a lens, magnifying and deflecting the light. This gravitational lensing effect causes the star to brighten, fade, and even shift position. Recently, a team led by Casey Lamb used this technique to identify a possible solitary black hole wandering through the Milky Way. By measuring the subtle lensing of a background star, they estimated the invisible lens to be between 1.6 and 4.2 solar masses. The experiment evoked the historic 1919 solar eclipse observations that confirmed general relativity, just as Eddington's photographs of deflected starlight reveal the sun's gravity. Modern microlensing surveys reveal the presence of dark companions. Even a stealth black hole leaves a gravitational footprint. Our ability to read that footprint means that a wandering black hole in our stellar neighborhood would likely be discovered decades or centuries before it reached the inner planets. Detection does not end with microlensing. If a rogue black hole were heading our way, it would first disturb the Oort cloud, the cometary reservoir at the far edge of the solar system. Astronomers expect that a passing black hole would send a shower of comets plunging toward the sun. That comet rain would be our first alarm signal, centuries or even millennia before the culprit arrived. As the black hole moved through interstellar gas and dust, material would spiral inward to form an accretion disk. Friction in the disk heats the gas to millions of degrees, causing it to glow in X-rays. A supposedly invisible object would become one of the brightest X-ray sources in the sky, easily spotted by observatories. In other words, we are not blind. Surveys like those of the Gaia mission, the optical gravitational lensing experiment, and the Roman Space Telescope continuously monitor stars for microlensing events. Early warning systems would give us centuries to marvel at the approaching visitor. The very fact that we have discovered nearby black holes like Gaia BH1 and BH3, which lie over 1,000 light-years away and are safely in stable orbits, demonstrates that our instruments are sensitive to subtle gravitational wobbles. A rogue black hole of significant mass would not sneak up on us. Many misconceptions surround black holes. One myth is that they act like vacuum cleaners, sucking in anything nearby. In reality, a black hole obeys the same gravitational laws as any other mass. If our sun were magically replaced with a black hole of equal mass, Earth would continue orbiting along the same path. The only change would be the loss of light and heat. Another myth is that agencies like NASA are hiding an incoming black hole. But such an object would be detected by its gravitational effects and the comet storms it induced, and no single organization could conceal it. The probability of a rogue black hole entering our solar system during the lifetime of our civilization is effectively zero. The nearest known black hole is more than 1,500 light-years away, and none are heading our direction. Comparatively, the risk posed by large asteroid impacts or solar flares is orders of magnitude higher. Recognizing these facts allows us to replace fear with informed curiosity. Black holes are not cosmic predators lurking in the dark. They're predictable products of gravitational collapse.